Hello everyone. Today I would like to present about my final year project. My final year title is Brownian motion of nanoparticles in nanofluid. My presentation is separated into several parts, including introduction, problem statement, objective, methodology, result, and discussion, and lastly conclusion. Now let's start. Nowadays, there are plenty of demands to enhance the convection heat transfer due to its wide application. Some of the passive techniques has been introduced such a long time, including geometry or surface modification, such as interrupt fins and surface roughness, and insertion of wire or turbulence promoters. Recently, some researchers confirmed that nanoparticles have the possibility to enhance thermal conductivity as well. One of the evidence is Kurma's research that proved that only 0.00013% of the AU, which is known as gold, nanoparticles are added to water, the thermal conductivity can increase about 20%. The thermal conductivity of nanoparticles is through Brownian motion, which is the irregular and random motion which plays an important role for energy transport. A numerical simulator has been developed under Asako. The simulator uses the principle of the dissipative particles dynamics, known as DPD, to simulate the motion of clusters of fluid molecules and nanoparticles, and heat transfer between the cluster and nanoparticle. The simulator can predict the thermal conductivity and dynamic viscosity of nanofluid without consuming long time and high cost compared to the experiment. However, the simulator is just newly built. Validation is crucial to make sure the prediction from the simulator is accurate. Thus, this project is done to become an evidence to support the simulator. For my FYP, there are three main objectives. The first is prepare the data from the past research paper for the validation of simulator that measure the motion of nanoparticles which conducted in water condition only. The second is compare and analyze the findings from different research papers. Last one is to study and compare the results between research paper and also some videos and result from the simulation. The methodology part will separate into two parts, where diffusivity is provided and diffusivity is not provided. First, the condition of diffusivity is provided. The first step is to analyze the characteristic of the nanoparticles. This will be the pre-setting for the DPD simulator. Then, running the DPD simulator coded by Fortran with a command prompt on the computer. After the simulation, a series of Fort files will be generated for plotting the graph. The iteration is set as 200,000 to reduce the simulation time. Before obtaining the gradient from the graph, as you can see from the graph below, the iteration is only set from 10 to 20, which is also equals to 100,000 to 200,000 iteration. The graph plotted is not from 0 iteration because the iteration from 0 to 100,000 is just for the nanoparticle to warm up in the simulation, which does not include any value. Thus, to prevent it from affecting the gradient, by drawing the best fit line, the graph is plotted with iteration 100,000 to 200,000 only. Last, compare the diffusivity result with the simulated result. Here comes to the second condition. The diffusivity is not provided. This mainly focuses on demonstrating how to find diffusivity from the video. First, convert the video into frames per second. In my case, 1 second is converted into 30 frames. When the video is converted into frame per second, the location of the nanoparticles can be tracked easily. Then, The distance of the nanoparticles is calculated out to plot a graph for obtaining the variance of Gaussian, S-square, and diffusivity. The S-square can be obtained through the last data of the graph from the line of best fit. After that, steps similar to the condition of diffusivity is provided, such as running the DPD simulator with information of the nanoparticles, plotting the graph, obtaining the gradient, and lastly comparing the diffusivity are carried out. For the result and discussion part, I would like to present the condition of diffusivity is provided first. Two research papers have been found, which are 6 nanometer quantum dots from Jeffrey Gusto and 500 nanometer fluorescent bead from Giuseppe Sancretaldo. The iteration for the simulation is set as 200,000, a normal presettings. However, the density and specific heat of the nanoparticles are set as default values because there is no detailed description mentioned in the research paper. The diffusivities from the research paper are 3.57, 10 to the power of negative 11 meters squared per second, and 9 plus minus 1.6, 10 power of negative 11 meters squared per second respectively. Then, the diffusivity from the simulation are 2.7555, 10 to the power of negative 10 meters squared per second, and 2.8975, 10 to the negative of 10 meters squared per second. The simulation results are calculated by the following equation, where uref is the reference velocity and RC is the cut-off radius of the nanoparticles. Meanwhile, the following part is the gradient value obtained from the graph after simulation. Here comes a special case that I want to highlight. For this research paper of 190 nanometers fluorescent bead from Matthew D.M., the diffusivity is not provided, but a series of images is shown, which same as frames per second. Firstly, the locations of nanoparticles are needed to track for calculating the diffusivity. Then, for the presetting of the coding, the density and specific heat of the nanoparticles are set based on its characteristics. However, the iteration is set to 600,000. In the first stage, 200,000 iterations is set. The obtained best fit line shows a declining trend, which causes the gradient and the diffusivity result to be negative values. However, the diffusivity should not be a negative value as it disobeys the law of the variance of Gaussian S-square, which should always a positive value. Therefore, the simulation is prolonged to 600,000 and an inclining trend is shown in the second image. The diffusivity from the analysis is 5.12, 10 to the power of negative 13 meters squared per second. Meanwhile, the simulation result shows a diffusivity of 3.3645, 10 to the negative 9 meters squared per second. For the video part, there are total 4 nanoparticles have been observed, which are 88 nanometer, 800 nanometer, 50 nanometer, and 240 nanometer nanoparticles. An important assumption is made before doing this analysis, which this video are believed that not recorded under fast-forward condition, which might make the diffusivity results inaccurate. Then, the presetting for the simulator is 200,000 iterations. The density and specific heat of the nanoparticles also set at default values because only the size of the nanoparticles are mentioned in the videos. Only the first 88 nanometer nanoparticles has been done 2 times analysis for 150 frames each, which equals to 5 seconds by tracking 2 nanoparticles in the video. It is believed that the more nanoparticles are analyzed, and the more accurate the diffusivity result will be. However, the other nanoparticles were only done for one-time analysis because only one nanoparticle are tracked in the video. The diffusivities result from analysis of location are shown in the third column, while the diffusivities result from the simulation are shown in the fourth column. Here comes to the conclusion part. The diffusivity of the nanoparticles obtained by DPD simulation was compared with experimentally obtained diffusivities in previous research. Next, the result between simulation and experimental one have some discrepancy. There are two possibilities that cause this situation, which are the results from the research paper might not correct as no strong evidence to support them, or the video shown might be played fast forward, or the experiment are done in an correct way, which did not mention in the description. Or the second one, the simulator still have some points to be improved in the future. And that's all from my presentation. Thank you.